Hello guys, welcome on Tesla Adventures. In this video, we are going to discuss the force acting between two parallel current carrying wires. You can see that there are two parallel current carrying wires kept like that, and they are carrying the current I1 and I2 in the same direction. The first wire will be creating a magnetic field on the second wire in downward direction, and the second wire will be creating a magnetic field on the first wire in the upward direction coming out of the plane. So they will be producing some magnetic force on each other, and we have to find out that force. So to find out that force, let us consider an element dl and another element dl on this one. And you can see that by Fleming's left hand rule, the force acting on this element will be like that, and the force acting on this element will be like that, df. Okay, and df will be equal to ILB. Now force acting on the first one is, let us suppose, df1 and it is df2. So df1 is I1 and L is dl, and B is magnetic field due to wire 2 on 1. So magnetic field of wire 2 on 1 will be mu naught I2 by 2 pi d. So df1 will be equal to mu naught I1 I2 dl upon 2 pi d. And in the same way, df2 will be equal to I2 into dl into B. Now B is the magnetic field of 1. So B will be mu naught I1 upon 2 pi d. So df2 will be equal to mu naught I1 I2 dl upon 2 pi d. Okay, so you can see that if we integrate these forces, then we have to apply the limit from 0 to infinity. So that would mean that the total force acting on each one of them will be infinity, and that is obvious result because the length of the wire is infinite. So the force acting on each of them will be infinite. Therefore, we talk about the force per unit length. So force per unit length acting on the first wire is df by dl, and that would be equal to mu naught I1 I2 by 2 pi d, and force per unit length acting on the second wire is df2 upon dl, and that would be also mu naught I1 I2 by 2 pi d. So you can see that these two forces are same, and therefore we can conclude that df1 will be equal to df2. Now if we talk about the directions, so we have already seen that if the current is flowing in the same direction, then these wires will be attracted towards each other. Force will be attractive like that, F1 F2. And if the wires are carrying current in different directions, then force will be repulsive. This is repulsive force, and this is attractive force. Okay, and now let us also discuss a problem in which we will discuss the SHM of a parallel current carrying wire, and it is placed on different fixed parallel current carrying wire. So there are two current carrying wires which are carrying the current in same directions. They are separated by a distance of d, and this wire is fixed, lower one is fixed, and upper one is in equilibrium due to the force acting on it by the lower wire. So when we will displace the upper wire by a small distance of x or y in the downward or upward direction, then it would start to perform SHM, and we have to find out the time period of that small SHM. So first of all, let us see that the force acting on the small element of this wire will be repulsive. In fact, it would be current will be in the opposite directions because it is in equilibrium. So current will be in the opposite directions. So force will be repulsive, and if we consider dF, then dF is the force per unit length. So dF will be equal to mu naught I1 I2 by 2 pi x. Let us suppose that this distance is x. We will substitute the value of x as d later on, but let us suppose initially that this distance is x. So we are just concerned about the additional force which is created due to displacement of the wire in the vertical direction, and that force is the restoring force which is responsible for SHM of this wire. So to find out that additional force, let us first of all differentiate this equation. D of dF upon dx, it will be equal to mu naught I1 I2 by 2 pi x square with a negative sign into dx, and this negative sign represents the fact that it is a restoring force. Okay, so this is the additional force which we have calculated, and this is the restoring force. So restoring force is equal to m into omega square x. Now this force is not the total force, it is the force per unit length. Therefore we will use lambda, which is the mass per unit length instead of mass. Okay, lambda into omega square into dx, where dx is the displacement given to this wire in the y direction. So cancelling out this dx with dx and cancelling out this minus with minus, omega square will be equal to mu naught I1 I2 by 2 pi. Now value of this x can be substituted as d, so 2 pi d square, and this is lambda, and omega will be root of this. So the time period, and omega is 2 pi by t, so time period will be equal to 2 pi under root of 2 pi d square lambda by mu naught I1 I2. This is the time period of SHM of this wire, which is above the fixed wire. Thank you.